Okay, so welcome back. I have a couple of things on the agenda today. Sorry, I haven't turned my camera on, my mistake. So I did this poll about whether to continue virtually or in hybrid. And the people that preferred, there was a slight majority in favor of continuing virtually. There were also some people that were very enthusiastic about switching to hybrid. When everybody had good reasons, I think. And there were some people who said, I'd like to try hybrid before expressing a preference. And so actually what I think I'm going to do is I think I'll give for sure I think I will give a hybrid lecture next Tuesday. Maybe even both lectures next week I'll do in the hybrid style. And even if we switch back to virtual after that, I thought it might be worthwhile for the students that are local and able to come to class to have a chance to meet each other and know who's in the class, and it might be a nice community building exercise. So that was my thinking. So at least Tuesday's lecture I will give in person in a hybrid style in Bain 6183 at the usual time. And then we'll see how it goes from there. And I probably ought to make this announcement. Maybe I'll make this announcement on the what do you call it? The content management system, Canvas, as well, for those that don't happen to be here right now. And I have posted the second assignment, which is due March 1st. I also, let me remind you that your project proposals are due on Tuesday. So I had said to email them to me, but I also set up a link where you can also submit them on Canvas if you like. And what else do I have to say? I think maybe that may cover. Oh yes. Hopefully the previous assignment, I've graded it and I uploaded it. Was anyone able to access the comments that I wrote on their assignments? Okay, good. So that worked properly. Good. And I have to clean up. So I got stuck at the end of last class, and so let me start by cleaning that up. So I will share a whiteboard. Whoops, I will share a whiteboard. Are there any questions before I try to fix where I was last class? Okay. So I wanted to prove this, what Villani calls the gluing lemma, and what Ambrosio, Brouet, and Simola call Dudley's lemma. Oops, come on. What's wrong? I'm not quite sure my let's try draw. Maybe this will work now. For some reason my my tablet is not seeing my pencil. That's going to be a problem. Drawing mode. Why can't I draw on the tablet?
It looked like it said something like that there's maybe like low battery. It looked like.
Yeah. No, in fact, I have two pencils, and the one that I usually use, for some reason, which I think is full, but let's check. 100%, there it is. Thanks, Nick. So normally this one works just fine, and I don't understand why it's not working right now. Draw. So when I use it to tap to draw, it recognizes it. But when I try to open one of the pencils, it doesn't seem to. Let me try stylus. Okay. I managed to change my stylus orientation, which I probably don't want to do, but this is very strange. So then I put this other pencil on there that was going to charge, that indeed it said it was out of batteries. But just to see whether the second one might work for me. I wonder what I can do. Maybe this is a, what do you call it? Somebody is sending me a message that they want me to use the chalkboard instead. What can I do? I could, I don't know what I could do actually. I mean, I could type, but that's not going to be very good. I've never had this happen before. Well, oh wait, there, no. So now I have a pencil up. Let's try drawing with touch. Well, I can write with my finger, I guess. Okay, let's try. I'll try writing with my finger. I don't know how this will go.
It's like kindergarten.
What's that?
It's like kindergarten. We're back to finger painting.
Oh, this. So now, oh, maybe it's okay. Let me try once more. So I got the second stylus to work. With the one that doesn't have any batteries. Let me see if I can get the first stylus to work. No, I can't seem to do that. All right, so let me try with this, the second stylus until at least until it runs out of battery. Okay, so right, I was trying to show this Dudley gluing lemma. Which basically said, if I have three measures, so let's say I have three measure spaces, they might all be the same space. And I have measures mu plus and mu minus and omega on these three spaces. And then I have a joint measure, which I think I called gamma 1, 2 with marginals mu plus and omega. And I have another joint measure gamma 2, 3 with marginals omega and mu minus. And we wanted, the claim was there exists a triple measure on the whole space such that the projection onto the first two variables is gamma 1, 2, and the projection on the last two variables is gamma 2, 3. And right, and so I said, well, let me disintegrate gamma 1, 2 in such a way that and basically what I was missing in this integrate gamma 1, 2 so that gamma 1, 2 of E is integral d omega on the middle space gamma 1, 2 y of E. And similarly, gamma 2, 3 of F should be integral on the middle space d omega gamma 2, 3 y of E. And the point here is, the picture is that the part that I was missing was when I'm doing, for example, M plus cross M, and I want to disintegrate gamma 1, 2, this measure here lives on a fiber y cross M plus. So gamma 1, 2 of y, even though, you know, you can think of it as being a measure on the product. M plus cross M, but in fact, it vanishes outside of the set y cross M plus, or rather M plus cross y. And so it's sort of secretly a measure on M plus, right? It lives on a copy of M plus. And so if another way to write the disintegration formula would be that if I had a function of x and y, and I was trying to integrate it against gamma 1, 2 xy on the product space, where f is arbitrary here, arbitrary continuous function, then I would have integral m d omega y integral m plus cross y, because the other measure vanishes everywhere else, fxy d gamma 1, 2y, and sort of y is a dummy argument, so I might as well think of this as being like an integral with respect to x. Okay, so somehow that was what I was missing. This insight that that even though this measure here lives on a product space, it really sits on a copy of m plus. It vanishes everywhere outside this copy of m plus. And so I said, well, define gamma tilde by its action on, using the Riesz theorem, by its action on continuous functions. And what definition do I want? I want the definition of fxyz d gamma tilde xyz over this triple space to be the integral over m d omega, the integral over m plus cross y d gamma 1, 2y of x, the integral over y cross m minus d gamma 2, 3y of z, and then f of xyz. And now a nice thing happens, which is that, for example, if I take f of xyz to depend on only the first two variables, then this becomes integral d omega. So first of all, this definition here is linear in f, and it gives you a bounded linear function. And so by the Riesz theorem, a gamma tilde exists. It gives you a bounded linear function on the Banach space of continuous functions normed by the sup norm. And right, if I take f to depend on only two of the variables, then I can bring f through the z integral, sorry, g rather. I can bring g through the z integral. It depends only on x and y. And now for omega almost every y, this is a probability measure and vanishes outside this set. So this integral is 1 almost surely. And so basically this formula we've seen before, this formula we saw right here, except with g replacing f. And so this formula is integral of g d gamma 1, 2. And since g is here an arbitrary continuous function on m plus cross m, we've just shown that the projection onto the first two variables of gamma tilde is gamma 1, 2. And that's what we wanted. So is everyone happy with that argument? And similarly, the same argument shows that gamma 2, 3 projection of gamma tilde will be gamma 2, 3. And so that's exactly what we wanted. Okay. So that ends the gluing lemma, or Dudley's lemma. And okay, so next up for today, and so that was the missing ingredient that I needed to complete the proof that that dp, this implies dp gives a metric, a distance on the set of probability measures on M with Pth moments. I mean, maybe, I guess there's one more thing. So if on M, if M is compact, and on PM otherwise, but I guess for this PM otherwise, what we would need to see that if you have two measures, mu plus and mu minus, that have Pth moments on M, you would hope that that implies that dp of mu plus and mu minus is finite. I guess we didn't check that. Let me see. It shouldn't be so bad to check it though. So I think that this follows from that. So I think that if you have a plus b to the Pth power, I'm thinking of p bigger than 1. I mean, maybe I should use convexity. So this is less than the max of AB, the 2 times the max of AB to the Pth power, which is less than 2 to the P, the maximum of the two guys. And the maximum is less than the sum. So I think I need that. And then this this implies that if gamma has marginals mu plus and mu minus, and I want to evaluate, I want to show that dxy p d gamma xy is finite. And I can, of course, estimate this by the triangle inequality. This is dxz plus dzy to the Pth power d gamma xy. And by this little inequality that I just showed, that's less than 2 to the P integral dxz to the P plus, well, this doesn't depend on y, so that's basically an integral of against mu plus. And then it would be integral dzy d gamma, but since that guy doesn't depend on x, that's like an integral against mu minus of y. And then this is finite if mu plus and minus are in pp. So in other words, what it meant to be in the probability measure sub p was exactly for any choice z that this integral is finite, and similarly this integral is finite because the other guys. Okay, so that told me that I had a metric on the space of marginals with these moments.
Robert, I think Ash has a correction in the chat.
Okay, sorry, I haven't been watching the chat.
Just in your inequality with a plus b to the p,
Yeah,
it should be a.
yeah, you're right. Of course,
Okay.
you're right. Right. So in fact, I was too quick. So I should have had max here. AB to the P. And that's of course less than 2 to the P, A to the P plus B to the P, because the maximum is less than the sum. Thanks, Ash. Other questions? Okay. So I wanted to talk, I'm going to talk a bit more about these metric spaces. It also occurred to me that I had some unfinished other business related to the conditions for regularity. So maybe I should do my digression into these into conditions for regularity, which and then I'll talk more about these metric spaces with the DP metric. So there's a couple of things I wanted to do about partial differential equations. So the first one I wanted to talk about is, so we saw that for the cost B is x dot y, and for measures d mu plus, d mu minus equal to f plus minus dnx, that basically the Jacobian, so in this case, G was gradient of a convex function, and the Jacobian determinant, which is of the approximate derivative, which is defined almost everywhere, is given by the ratio. I can take the absolute value signs away because U is convex. It's given by the ratio of f plus x over f minus x, f minus g of x, so f minus du of x. And so if on the other hand, B satisfies more generally, if A1 and A2 hold, then what we know is that, so let me draw the picture once more. The picture was, we have a U, which is its own second transform under B. That means at each point x naught, we can find a choice of y such that B of x y naught minus lambda naught just touches U from below. And that tells us that assuming all the derivatives exist, that du of x is equal to dxb, this would be at x naught now. And second derivative of U at x naught dominates second derivative of B at x naught y naught. And so this is of course the Monge-Ampere equation. I thought it would be good to write down what the Monge-Ampere equation looks like for these more general surplus functions. And so and it's enough to be in the, or approximately twice differentiable at x naught. And so to get the analogous equation to this fellow for one of these more general surplus functions, benefit functions, you basically, well, of course, so the first equation would, by the twist condition, tells you that y naught would be g of x naught given by some capital Y of x naught du of x naught, where capital Y is the inverse operation to this one. And so the first condition, the first order condition, can also be written in the form du of x equals dxb of xg of x almost everywhere. And since this Monge-Ampere equation comes from it's the Jacobian determinant of the map, if you want to get the Jacobian of this map G, you want to differentiate this equation with respect to X. So you do this component-wise, but let me be schematic rather than doing it by components. So schematically, you'd have the second derivative of U would be given by the second derivative of B with respect to X, plus by the chain rule, there'd also be a second mixed derivative of B with respect to XY, and then you'd have the derivative of the mapping G. Again, this would hold almost everywhere because these second derivatives, U is twice approximately differentiable almost everywhere. And so I want to isolate the Jacobian. And I can do that because, so to isolate the Jacobian, I can write the Jacobian in the form d2u minus dxx 2b times d2xy b inverse, and that would give me dg. And so this should still hold almost everywhere. And there's no problem inverting this matrix because of A2. Tells me that matrix is invertible. And then notice because of my second order condition, this matrix here is non-negative definite. And so the determinant of dg in absolute value would be the determinant of d2xyb inverse in absolute value times the determinant of d2xyux minus dxxb. And this is the thing that would be the ratio of the initial density to the final density. And so if I wanted to write this in sort of a more PDE kind of form, I would write maybe determinant d2u minus d2xxb, and then this would be evaluated at xy is x comma capital Y of x du would be equal to determinant of d2xyb times f plus of x over f minus of y. And again, this would be evaluated at the same point at xy is x capital Y of x du. So the terms on the right-hand side here, they depend on x and grad u of x, but they don't depend on u or the Hessian of u. And the terms on the left-hand side, the Hessian only appears here, and then this is some lower order term that depends on gradient of u. So this is what's called the Monge-Ampere type equation. And in some sense, our optimal transport argument tells us that when f plus and f minus are arbitrary non-negative probability densities on a bounded set, then this Monge-Ampere type equation has solutions, at least in the almost everywhere sense. And not only that, it has solutions U, which are their own second transform under dB tilde. In almost everywhere sense for arbitrary, compactly supported probability densities. And I have some other remarks. So what's the other remark? The other remark is that this equation is so-called degenerate elliptic. And that basically follows from the non-negative definiteness of what's under the determinant. But let me show the degenerate. Let me formally argue the degenerate ellipticity, but let me just do it for the regular vanilla Monge-Ampere equation, not for the Monge-Ampere type equation. So what does it mean to be degenerate elliptic? It means when you fix a solution U naught and you perturb around that solution, or maybe I could write U plus SW, maybe that's better, S being a real number here. You want to linearize this in S. So let's see. So the vanilla Monge-Ampere equation was determinant of Hessian of U of X equal to F plus of X over F minus of du of X. And so imagine I had, imagine I wanted to perturb around a solution. So I had d2u plus s d2w equals something. So this would be equal F plus of X over F minus of X. I could make my life simple by taking F minus be a uniform on some set, so that the denominator would just be 1. But I can do it anyways, du plus s dw of X. And so I want to linearize this equation. And so how do I linearize it? Well, this is determinant of d2u of X. Let me do a formal calculation. Times the determinant of the identity plus s d2u inverse of X d2w of X. And so formally, at least, that's determinant of d2u of X. So the determinant of the identity is 1. And then if S is very small, then the first order correction to 1 is S times the trace of d2u of X inverse d2w of X. And then the determinant's a polynomial in S of degree n if we're in Rn, and the next order term would be order S squared. So in particular, if I took the derivative with respect to S of this equation and set S equal to 0, I would get some left-hand side, which do I want to figure out what the left-hand side is? I'm not sure I do. So the left-hand side, I guess, is something like minus F plus of X over F minus of grad U of X to the probably square, and then maybe derivative of F minus of grad U of X dotted with dw. And then this would be equal to determinant of d2u of X trace d2u inverse of X d2w. And if the thing I'm perturbing around actually solves the equation, so if d2 of X equals the ratio of F plus over F minus composed with grad U, then that's telling me that this term here exactly cancels the numerator here and 1 power in the denominator. And so then the equation I get in the end would be trace of d2u of X inverse d2w. This is, so what's the, is, I guess, minus derivative of log of F at grad U dotted with dw of X. And so what's to notice about this equation is that it's nonlinear in U. It may be nonlinear in U. but linear in W. Right, so the nonlinearity would come here in U, that the log of F composed with grad U. But I don't care about the nonlinearity and also the inverse. This inverse matrix is very nonlinear in U. I don't care about the nonlinear in U. What I care about is the linearity in W. And this term is lower order in W, so I don't worry about it too much. The second order term in W is over here. And you're supposed to think of this as if Hessian of U was the identity matrix, this would be Laplacian of W. If Hessian is not the identity matrix, the convexity of U, convexity still implies that the Hessian of U has a sign. And so this is more like, it's still more like Laplace's equation than it's more like Laplace's equation or Poisson's equation than it is like the wave equation or the heat equation. But if I knew, let me switch back to black. If I had bounds like epsilon identity is less than Hessian of U is less than 1 over epsilon identity, then this trace is what would be called a uniformly elliptic operator, because the coefficients in front of the Hessian of W are given by a positive definite matrix, bounded matrix. And that basically means that if I actually were able to prove this, so if I already knew that U was twice continuously differentiable and satisfied bounds like this, I'd be able to get estimates on W that would tell me some stuff about higher order differentiability of U. So I can bootstrap higher differentiability of U in C2 alpha using linear elliptic theory for W. Right, so once I know U is C2, I know, well, there's one more bit of information that's kind of interesting. So if you have an upper bound for Hessian of U, like you would get when U is C2, then the determinant itself, if you think about the right-hand side as being something like 1 or some constant bounded away from 0 and infinity, the determinant itself will convert an upper bound to a lower bound. You can't, if U is upper bounded, you can't, and if all of the eigenvalues of Hessian of U are upper bounded, you can't have any of them going to 0 without the determinant also going to 0. So if F plus and F minus are bounded away from 0 and infinity, then the lower bound follows from the upper bound. And the epsilon is something like 1 over the upper bound for U. Maybe there's an n-1th root somewhere, or an n-1th power. So somehow, because of the equation itself, an upper bound because the equation involves a product of eigenvalues, an upper bound for those eigenvalues turns into a lower bound for those eigenvalues. So the challenge in regularity theory is always to get the first 2 plus alpha derivatives, at least for these kinds of equations. Okay, so that's basically what I want. And even if you don't have this, what you still have is du is non-negative, and then we say it's not uniformly elliptic, but it's degenerate elliptic. And basically the difference is that for uniform elliptic equations on a domain subject to boundary conditions, they behave like Laplace's equation. So even if the boundary conditions are rough, the solution on the interior will be smooth. For degenerate elliptic equations on a domain, that's not true anymore. If the boundary conditions are rough, the roughnesses will propagate into they have the potential to propagate into the interior. Okay. So that was one story I wanted to tell you. before leaving the topic of partial differential equations. And the other story I wanted to tell you, because I decided to put a question about the A3 condition on the assignment. So I wanted to remark that I wanted to tell you how to compute computing A3. So remember, A3 involved, A3 said something like, if the fourth mixed derivative, 2 with respect to s and t, of b at xs, yt should have a sign if at 0, if the second derivative b xs yt vanishes at 0, and if either or the symmetric condition on S. And so let me just mention how to compute these geodesic equations and how to compute this quantity here. So you've seen it once. So so let's say 1 or 2. So how does 1 look? Well, if I write rather bi for xi, x0 yt, and I take d by dt, then I'm going to have bi comma, so b derivative xi yj at y dot rather j of t, and if I take another derivative, then I get 2 terms. I could get a bij comma y double dot j, and I also get a term of the form bi let's call it kl y dot k y dot l. So this is somehow this geodesic equation, this funny metric I wrote down, and if let's say BNM denotes the inverse matrix to BMI, so that this is like delta NI, then I can rewrite this geodesic equation by multiplying by the inverse of this matrix to get something maybe more familiar looking. I could get something like y double dot m plus b I m b I k l y dot k y dot l. So somehow that's the B segment equation. Maybe I should try to make my double dots legible. And if I want to think about what this guy looks like, there's going to be, well, let's do the computation. So the claim is that A3 holds if and only if a certain tensor, which looks like Bij KL, it looks like these mixed fourth derivatives, but then there are some third derivatives involved. So something like Bij M, BMN, BNKL. And then you'd have your tangent vector in the y direction. So like the x direction. So something like x dot I, x dot j, y dot k, y dot l is bigger than 0 whenever I need the second order condition as well, this condition here, but that one's simple. Whenever x dot I, bi, comma j, y dot j equals 0. So this is a more tensorial representation of A3 because I don't need to talk about curves anymore. I just need to talk about a point 0 and a tangent vector in x at that point and a tangent vector in y at that point. And they need to be orthogonal to each other in this sense with respect to this matrix V. And so the point I wanted to make is, where does this thing come from? It comes from taking the 4 derivatives of this, and it's pretty clear you're going to get this term from those 4 derivatives, but you're also going to get some terms involving x double dot and y double dot, and then you need to use the 2G, either this equation or the symmetric. So this equation here, or the symmetric equation for x, to get rid of those x double dot or y double dot terms. And then when you get rid of those terms using the geodesic equation, the B segment equation for either y or x, that's when you get these corrections here. And you might expect there to be actually 3 corrections, 2 with negative signs and 1 with a positive sign, but 2 of them, they're all the same correction. So when you add them up, you get just this 1 correction. So I don't know if anyone wants to see that calculation or not. Maybe not. Questions? Is it clear, at least in principle, how this calculation would go? Okay. All right. Right, so back to my, so back to my space, the probability measures on M with Pth powers and the distance dp. So, so a natural question is, what topology does dp metrize? And as usual, it's a little bit easier to answer this question if M is compact. And the right. So if M is compact, so there are a few things to remark. The first one to remark is that this, so far I'm not really using compactness, but so remark the map P is monotone, is non-decreasing in P. And that's basically by Jensen's inequality. And let me do a simple case of it. So for example, I want to show D1 is the smallest of all these distances. So what is dp? Well, dp of mu plus mu minus is, to the Pth power, is the minimum overall gamma having mu plus and mu minus as marginals of integral dxy to the Pth power d gamma. And so let gamma 1, for example, be the argument when P is 1. And so then I get an upper bound for this. This is certainly less than the Pth power of the distance when I integrate against gamma 1. And now Jensen's inequality tells me that if I integrate first, I should get something smaller. So this looks like it's going the wrong way on me. So what do I want to say? I want to say this is this less than the integral of d gamma 1 raised to the pth power. And it looks like Jensen's going backwards. Am I doing something wrong? Maybe it's not increasing in p, but that doesn't strike me as the right thing. Wait. So I want to get W. Oh yeah, wait. No. So what's my claim? My claim is that is D1 is less than dp. So I'm already going about this. So clearly I'm already going, if I want D1 to be less than dp, I'm somehow going about this the wrong way because somehow what I'm driving here is an upper bound for dp. So I should have, I should probably do the other thing. I should rather say, I should let gamma p be the argument for dp here. And then d1 of mu plus mu minus is of course less than the integral of d to the 1th power against gamma p. Because this is a test, it has the right marginals to bound this guy. Great. And so I can raise both of these things to pth powers. This looks better. And then by Jensen's inequality, I can bring the pth power inside. That's much better. And this, because I chose gamma p to be the argumentizer for here, this is by definition the pth power of dp, and so therefore d1 is less than dp. Great. And by the same argument, you could show that dp is less than dp plus epsilon. Only the same argument, only slightly more confusing notation. So this basically shows the monotonicity of d with respect to p. And on the other hand, if I'm dealing with a space whose diameter is finite, so I don't know what to call that, capital D, the diameter of M, I'm going to get an upper bound for dp in terms of d1, not a linear upper bound for dp, but a nonlinear upper bound for dp in terms of d1. Then dp mu plus mu minus, which is equal to what's less than or equal to integral of dxy to the pth power, let's say d gamma 1. I can control that by, sorry, this would be the pth power of this. I can control that by p minus 1 powers the diameter times the integral of the first power of the distance against the minimizer for p equals 1, and that's dp minus 1 d1. And so if I now take the pth root, great. So basically what this inequality shows me is that at least, so first of all, it shows me that convergence in dp implies convergence in dq for any q less than p. And secondly, it shows me that if I'm working on a bounded space, a space of bounded diameter, then convergence in d1 is equivalent to convergence in dp. dp metrizes same topology as d1. And so what topology is that? Well, so another nice thing that happens, so it's a topology of weak convergence, but weak convergence against what? And so we talked about if M was non-compact, then there was a difference between so narrow convergence holds of, let's say, uk to mu infinity, holds if and only if integral phi d mu k converges to integral phi d mu infinity for every phi in continuous bounded. And what's called wide convergence or weak star convergence holds if and only if the same thing holds, but for every phi in a slightly smaller class of functions. So you can take it to be either compactly supported or vanishing in infinity. I mean, the advantage of this is it's closed under the suit norm, but this is dense in that fellow. So at least if the space is locally compact. These are equivalent in a locally compact sigma compact topological space, Hausdorff space. Metric space. Hausdorff spaces are a general relation of metric spaces. And so, and obviously, but there's obviously more of these test functions here. They're continuous bounded functions which are not compactly supported and don't go to 0 to infinity. And so narrow convergence is a more restrictive notion because you need this convergence to happen against a slightly bigger set of test functions. And then, in fact, what's true, even better, is that that narrow convergence and wide convergence are also equivalent under these compactness, these local compactness hypotheses. So now I'm quoting a lemma from Sant'Ambrogio's book. Which is basically if M D is locally and sigma compact, then narrow and wide convergence coincide. So I actually am not that familiar with the term wide, but for sure, so probably it's, let's put it weak star down here. For sure, weak star convergence is convergence against these kind of test functions. And so probably wide convergence is convergence against these kind of test functions, which is a slightly smaller test set again, although they happen to coincide in this setting. And so it's going to turn out that what dp is metrizing, if the space is compact, is narrow convergence or wide convergence or weak star convergence. Take your pick. They're all equivalent. I.e., convergence against the compactly supported guys implies against the bounded guys as well. And so this is just a monotone convergence theorem argument. It's nothing deep. So you take your favorite bounded guy and you want to show it can be approximated by a compactly supported guy, and that's where you use the sigma and local compactness. So by sigma and local compactness, and in Eurozone's lemma, Eurozone's lemma is the one that says anytime you have a compact set contained in an open set, you can find a function that's 1 on the compact set and 0 outside of the open set and continuous. Oh yeah, sorry. Before I do this, I want to, since phi is bounded, then phi plus some constant is bigger than 0. And so let me add that constant to phi. And then by, I should, oh yes, let me be careful about the statement of the theorem too. So there's a pitfall in this theorem. On probability measures on M. And I'll come back to this pitfall. So in other words, why am I harping on probability measures? So you can have a sequence of probability measures which converge to something weakly. If I was not in a compact space, if I were in a space which was just locally in sigma compact, like Rn or like the real line, I could take a sequence of Dirac measures walking off to infinity with weight 1. And that sequence would converge to 0 against compactly supported test functions, but it would not converge to 0 against bounded test functions, because its integral, if you take a constant test function with constant value 1, the integral of every Dirac measure with mass 1 against that constant is 1, but the integral of the 0 measure against that constant is 0. So if I was talking about convergence of probability measures to something not a probability measure, then narrow and wide convergence are different things. But if I'm talking about a sequence of probability measures and a putative limit, and then the question of, which is also a probability measure, and then the question of, does this sequence of probability measure actually converge to this limiting probability measure, then narrow and wide convergence are the same thing. And we'll see that that has to do with the addition of this constant somehow. When I'm integrating against a probability measure on both sides of an equation, when I add a constant test function, it adds the same amount to both sides of the equation. When I'm integrating against two measures with different masses, you add a constant to the test function, it changes the two sides of the equation. Okay. By sigma and local compactness in Eurozone's lemma, you can find, so there exist compactly supported test functions, cutoff functions. I called them chi-n in my proof, and they should converge. They should be an increasing. So chi-n is going to be less than chi-n plus 1, and as n goes to infinity, they should converge to 1. So monotonically. And then you just set your approximation phi to var phi or whatever psi. So these are non-negative functions. And they converge monotonically because of this limit, they converge. Sorry, it's wrong. My pencil just died, I guess. Yeah, I'm back down to 0 charge. I wonder if I can, let me try the other pencil once more. I wonder if I can get it to work. Yeah, oh, wait, I'm getting something. Okay, great. This is the pencil that actually has some juice. But I guess the problem is that once I try to charge the other one, this one disconnects somehow. I'm learning about my iPad. Wait, what happened? Yes, I was in this lecture. You go down. This one has some juice, but it doesn't want to write. Why doesn't it want to write? There we go. Okay, so this now converges upwards to phi plus c. And so the Lebeg monotone convergence theorem tells me that the integral of var phi plus c against mu is the limit as n goes to infinity of these approximate guys. And these approximate guys are compactly supported. So if mu k converges to mu narrowly, widely rather, in the more relaxed notion, then I can write this as the limit as n goes to infinity of integral of, or maybe another limit, lim k goes to infinity of integral phi n d mu k, because the phi n's are compactly supported, so I only need convergence against compact support functions, which is the weaker notion. And on the other hand, the phi n, because it's increasing towards this limit here, then this is less than the lim inf n goes to infinity, k goes to infinity of integral phi plus c d mu k. But now this thing is completely independent of n, so I can forget about the n. And now, because I have probability measures on both sides of the equation, the c is irrelevant. And so therefore I've shown that phi d mu is less than lim inf k going to infinity of phi d mu k. And if I applied the same argument to minus phi, I would get that integral phi d mu is bigger than lim sup. You know, I can add a constant to this to make it positive again, apply the same argument. And then so I would have shown that by using that it converges, sorry, this was poor notation. I should have said, let me call this phi. So by using only convergence of compactly supported test functions, I eventually derive these two inequalities, which tell me convergence against a non-compactly supported, but still bounded function. And it was important that they were bounded so that I could add constants to them to make them positive. Are there any questions? Okay, so as long as I'm talking about just a sequence of probability measures and a putative limiting probability measure, narrow and wide convergence and weak star convergence are all the same thing, provided my space is locally compact and sigma compact, so that I can get these approximating functions, compactly supported approximating functions that do what I want. So the theorem then, which I guess I'm going to prove it on Euclidean space, is this is theorem 5.9 in Sant'Ambrogio's book. Euclidean space is, of course, both sigma compact and locally compact. So if I have a compact subset of Euclidean space, or I guess, then mu converges in whichever of these weak star, mu n or whatever, mu n converges to mu infinity in any of these weak topologies, let's say weak star, because narrow, it's the same as narrow and wide and whatever. If and only if W1 of mu n mu infinity is 0, goes to 0. And of course, that's equivalent to the limit as n goes to infinity of WP mu n mu infinity being 0, as we already saw.
Oh, and Robert, W1 and WP are just the Wasserstein distance, right?
I'm sorry, I switched notations, didn't I? I guess I switched to San Ambrosio's notation. So let me come back. Yes, yes. So some people write W, I'm usually writing D. Any other questions? And so so San Ambrosio's proof, basically it works in Rn because, so the idea is to use the duality, the Kantorovich duality that we saw last class for functions of the distance, for the distance cost. And so recall that call D1 of anything of mu n infinity, I guess, can also be written in the form sup over Lipschitz 1 functions phi of integral phi d mu n minus d mu infinity. That was what we saw last class, and that's going to be our main tool for showing this. So if D1 of mu n mu infinity goes to 0, then given some phi, whatever you like, compactly supported test function on M, of course, it may not be Lipschitz, but I can define phi epsilon to be phi convolved with your favorite mollifier. And so phi epsilon, of course, is 1 over epsilon to the n, phi 1 of x over epsilon. And where phi 1 is some compactly supported smooth function integrating to 1. And then I know that this is going to converge. It's standard that this converges to phi uniformly as epsilon goes to 0. And the other thing is that phi epsilon is C infinity and compactly supported, and so in particular it's Lipschitz. And so I have D1 mu n mu infinity, which is going to 0, is bigger than the integral of phi epsilon d mu n minus mu infinity for every epsilon. Oh no, wait a minute. It's Lipschitz, but its Lipschitz constant could be larger than 1. So so let me divide this by the Lipschitz constant. So this I know is going to 0. So in fact, this is to 0 as n goes to infinity. And right, so for fixed epsilon, this goes to 0 as n goes to infinity. And so it's also true for fixed epsilon that this goes to 0 as n goes to infinity. But the difference between phi epsilon minus phi d mu n minus mu infinity is controlled by 2 times the sup norm of phi epsilon minus phi. And so given delta, for every delta bigger than 0, choose epsilon such that 2 the sup norm of phi epsilon minus phi is less than delta, and then choose n large. N large implies integral phi epsilon d mu n minus mu infinity is less than delta. And then you combine these two things and you get that the integral of phi d mu n minus mu infinity is less than 2 delta. And since delta was arbitrary, taking n large enough depending on delta shows that this limit, the limit I wanted, goes to 0. So that's one direction. That's sort of the easy direction. If you have convergence of the Wasserstein norm, then you have convergence against these compactly supported test functions, continuous compactly supported test functions. And conversely, if mu n goes to mu infinity widely, I want to show the Wasserstein distance converges. So let me assume that I need some number, let k, no, let k be, let L be the limit, or let me the lim sup as n goes to infinity of the Wasserstein distance, the one Wasserstein distance between mu n and mu infinity. And let me take a subsequence so that I actually converge to this lim sup. And I'm required to prove that L is 0. That's what I'm trying to show. And on the other hand, I know by this Kantorovich duality that I recalled up here, for each nk, I want to choose a one Lipschitz function attaining the maximum. Now phi k would be fine, such that d1 of mu nk mu infinity and now I want to take the limit as k goes to infinity. So these are equi-Lipschitz functions. So they're so Ascoli-Arzela a further subsequence, which I won't reindex. Phi k converges to a limit phi infinity uniformly. Oh, well, wait a second. Let's fix some. You want to fix x naught. So I need, for Ascoli-Arzela, I need the functions to be equicontinuous, but I also need them to be uniformly bounded. So fix x naught in M and set phi tilde k of x to be phi k of x minus phi k of x naught. And so I've now normalized the phi tildes all vanish at x naught. And they're all Lipschitz with Lipschitz constant 1. And the space is compact, so it has bounded diameter. So they're all bounded. And they all vanish at the same point. So they're now uniformly bounded. So there's a further subsequence. And of course, subtracting this constant here doesn't, since these are both probability measures, again, I can add and subtract any constant. So I can put the tilde in here if I want. Great. And that further subsequence converges to a limit, which also vanishes at this point x naught. It converges uniformly by the Ascoli-Arzela theorem. And so I have d1 of mu nk, mu infinity is integral m phi tilde k d mu nk minus d mu infinity. And these guys are converging uniformly. So so if I write this in the form phi tilde k minus phi infinity d mu nk minus mu infinity plus integral phi infinity d mu nk minus d mu infinity. Now as k goes to infinity, this converges to 0 because I assumed wide or equivalently narrow convergence, and this is a continuous bounded function. And as k goes to infinity, this term goes to 0 because these measures have, this difference has total mass 2, and this is going to 0 in the uniform norm. So because this is going to 0 in the uniform norm, and these measures are bounded in mass, this side goes to 0. And so that shows the whole thing goes to 0. And this was, that shows this limit was exactly the L that I wanted to show was 0. Does that make sense? Okay, so that is a good place to stop. Any questions before I turn the recording off? So for those who weren't here at the beginning of the hour, so what I said was the results of the survey was that there was a slight majority in favor of continuing purely virtually, but there was a significant minority in favor of switching to hybrid. And so what I said was I will do a hybrid lecture on Tuesday and possibly also on Thursday next week, partly to see how it goes, because there were 1 or 2 people that said, let me check out the hybrid and see how it goes. And partly because even if we switch back to virtual after that, it gives you a sense, to those of you that are able to come to the in-person lecture, get to meet each other, and hopefully it will give you some sense of who else is taking the course and create a local community for those of us that are actually in Toronto. Any questions? Project proposals are due Tuesday, and the next assignment's posted. There was a slight clarification, so I posted the next assignment 2 days ago, but I loaded an update today. So if you downloaded it 2 days ago, you might want to download it again, and it's due on March 1st. And I will now put the recording on pause and we can transition to office hours.